Okay, today we're going to talk about the abstract concept of differentiability. Differentiability is a fancy way of saying a derivative exists. So let's write that definition. A function f is said to be differentiable at a point A, let's say x equals A, if the limit as h goes to 0 of f of a plus h minus f of a divided by h exists. Right? If you recall from our first chapter, sometimes limits don't exist. Right? Sometimes limits just do not exist. And when the limit that defines the derivative does not exist, then the function does not have a derivative at that point. Okay, there are basically three situations leading to a lack of differentiability, at least in this class. Okay, the first situation is the function is not continuous. At a point. The second situation is that the graph has a corner at a point. And the third situation is that the graph has a vertical tangent. That would, of course, be an infinite slope, and if the slope was infinite, then the limit which defined the slope would be infinite, and we don't allow for infinite limits, so we would say the limit doesn't exist. So an example of what we're talking about here, this would be like a function that jumps like this. There's no way you can have a derivative at the jump, right? That limit's not going to exist. A corner point, an example there, is something where something's happening, but then sharply it turns in some other way. And the vertical tangent would be something like this. And the places where the derivative doesn't exist, right, are here, here, and here, right? The tangent line would be vertical. What would the tangent line for this second one be? Is it that line or is it that line, right? There's no unique way to say it. And what would a tangent line even mean when there's a jump, right? So those are the three things to look out for if you're looking at a graph in terms of differentiability. Okay, now let's take some examples and compute with them. Let's look at this function. F of x is equal to 2x if x is less than or equal to 1, and 1/2 x plus 3/2 if x is bigger than 1. And let's look at differentiability when x is equal to 1. Right. So if we wanted to take the derivative of this function at 1, we would take the following limit. The limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h, right? That's the definition of the derivative. The issue is, right, the issue, which is slightly subtle, is that this limit is as h goes to 0. That includes both positive h and negative h going to 0, right? Limits are two-sided. But when h is positive, that would mean we would be using this version of the function for when x is bigger than 1. When h is negative, we would be using the other version of the function. So if we want to calculate to see whether this limit exists, right away we have to split it into two different one-sided limits and see if they agree. The limit from the right and the limit from the left. . Okay, let's look at the limit from the right. That's when h is positive, which means we are in the second form of this function that was written down. We're at the 1/2 x plus 3/2. So it'll be 1/2 1 plus h plus 3/2 minus 2, because f at 1 is 2. And then we divide by h. And just to save space here, when you calculate this, it comes down to being exactly 1/2. Now let's look at the lower limit. From the left-hand side, we have the limit as h goes to 0. From the left of this time, we're using the 2 times x version of the function. F of 2 is still 2. And we will be taking this limit. Right? This limit is equal to 2. Since the right and left side limits do not agree, we would say here the limit does not exist. So f is not differentiable at x equals 1. What's going on there? Okay, well, basically what's happening is we have a function which has a slope of 2, and then at 1 it switches to being something that has a slope of 1/2. This is x equals 1. That's what the picture looks like near x equals 1. And so this is our second possibility that we discussed above when we have a corner, right? So this is a situation which led to a corner. Okay, we'll explore a few more in the worksheet. I want to look at some special cases, though, where we actually have to look at a graph very carefully. Example. Let's look at f of x is equal to x times sine 1 over x when x is not equal to 0, and 0 when x is equal to 0. Okay, we're going to look at differentiability at 0. That would mean taking the following limit. The limit as h goes to 0 of h sine 1 over h minus 0 divided by h. That would be what happens when I get f at 0 plus h. Right? If you're confused where this came from, this is f at 0 plus h. This is f at 0. Right? So when I look and cancel here, I get the limit as h goes to 0 of sine of 1 over h. And if you recall from before, that doesn't exist. That was that thing that oscillated infinitely many times near 0. So this is not differentiable. Okay, let's look at a similar example, though. Here we're going to have f of x is equal to x squared times sine 1 over x when x is not equal to 0, and 0 when x is equal to 0. We're going to again look for the differentiability at 0, and we would find, okay, I want to take this limit. This is going to be h squared sine 1 over h minus 0 divided by h. And now I have the limit as h goes to 0 of h times sine 1 over h. The sine 1 over h thing oscillates like crazy, but this h, right, this sine 1 over h is trapped between -1 and 1. And that h goes to 0. By the sandwich theorem, we would get that this limit is equal to 0. And so the derivative does exist. So let's look at some graphs of these functions and see what's going on here. Okay, there we go. Okay, let's plot x times sine 1 over x. Okay, let's see what this picture looks like. This is the one that didn't have a derivative at 0. Okay, looking at this picture here, you can see that there would be no real way to have a tangent line with this function, right? It looks like you could pick any line with a slope between -1 and 1, and it would be equally good as a tangent here. So there's not a unique tangent line. What's going on that's different when we add the x squared, though? That's probably worth looking at here. Now you see that x squared squishes it in enough so that the function is really flat near 0. And we really do get a derivative there. Even though we have all these squiggles, we still have a derivative. This is just because the derivative is defined to be a certain limit, and since a certain limit exists, the derivative exists. Okay, there's one theorem in this section that I want to talk about. It's as follows. If a function f is differentiable at x equals a, then f of x is continuous at x equals a. So differentiability implies continuity. Now, the other way around does not work. Continuity does not imply differentiability, which we saw above here. This example, let me circle it here. This example here was a continuous function that was not differentiable at that point. So differentiability, or continuity, does not imply differentiability, but differentiability does imply continuity. How can we see that? Let's just show a brief proof here. Don't get too nervous. Okay, the function is continuous if I can show this limit is 0. Right? That's another way of phrasing continuity. So if I could show that the function f of x goes to the value f of a as x goes to a, then the function is exactly continuous. All right, well, let's look at this limit. That's equal to the following limit. X minus a times f of x minus f of a over x minus a. I've multiplied by x minus a, but I've also divided by x minus a. And remember, we're not plugging in x equals a. This is a limit. We're never plugging in x equals a. And so this is a perfectly valid thing to do. I'm not dividing by 0 because x is not allowed to be a. Now I could use one of my limit laws to say this is the limit as x approaches a of x minus a times the limit as x approaches a of f of x minus f of a over x minus a. I can split my derivative, I can split my limit into two limits. This first limit is 0. The second limit is actually the definition of the derivative at a, which, since the function is differentiable, exists. This is the x goes to a definition of the derivative, not the h goes to 0 one, which we mentioned briefly, but haven't used yet. So now this is 0, and we showed what we needed to show. So indeed, differentiable functions are automatically continuous. If there is a tangent line, then the function is continuous at a point. All right. I hope that this made sense, and good luck on the worksheet.